Yeah, thank you for the introduction. As mentioned, I'm Logan Campbell, founder and CEO of Aerotas. We have been around since 2014, which is not super long in the survey world, but about as long as the drone industry's been around. So that's from that perspective, we've got a lot that we've learned from going through this whole drone surveying process, and they're here to share it with you. So we've got a pretty full agenda actually today of stuff that I want to cover. We've got a whole bunch of content, but overall what we're going through today is the actual complete office workflow for drone surveying. So we're not going over the actual field side. We're not going to talk about autopilots or something like that. We're going to talk about the process from actually saying, all right, you've flown your drone, you have your 1,000 photos, what do you do with them? Because anyone that, so here by show of hands, how many people are actually flying drones right now already for work? And how many are flying drones regularly on most projects and actually using them to get topo data? All right, still a good number. So we'll go through our workflow that we've developed to help with that through photogrammetry, getting your RTK, PPK data integrated, measuring and reporting accuracy for your surveys, how to draft Linework on top of those photos, finishing it in CAD, and then creating a complete workflow that actually saves time and money. So just a little bit about us at Aerotas. We turn drone photos into survey data. That's our business. We'll take photos and turn them into Linework for you, and we've got hundreds of surveyors all across the country that we do this for. So what I like to start with is, what's the end goal of this? What's the end goal of having a drone survey program to begin with? Well, the first thing is obviously going to be better deliverables, right? You want to get something that is better than your previous survey might be. So that just might be having the same thing, but with an orthophoto backing, having that context for the engineers that you're delivering it to, for your clients having nice, pretty photos. But also, there are two other really important ones to me: save time and save money. If you're doing a drone program that all it does is gather pretty pictures, it's probably not doing its job. You need to save time and save money, and that means creating an efficient workflow and not just trying to throw money into a black hole and hope that eventually somehow it's going to improve. Because for us, you put all this together, what the end goal is something like this. It's a survey, right? And you can't really tell if this was gathered by drone or what part was by drone and what part was on the ground, whether it's a drone photo, satellite photo, it doesn't really matter. The end deliverables for you should look the exact same whether you're using a drone or whether you're not, but they should do it in less time and less money. So one of the things that I'm going to hammer on, because today is not about how do you spend 500 hours on a single project to get the best possible, most detailed data on a single drone survey. What I'm going to talk about is how to get this in an efficient manner. So for me, I always say if your drone program isn't saving you time and money, it isn't working. It's not a drone program then. It's a research program. It's a fun side project to say, ooh, fun, look how cool this technology is, look what we can do with it. But a good drone workflow should save you time and money. So the overall step that the kind of 6 steps that we like to break it up into for these projects, how do you actually get from drone to Linework? The 6 steps are: you plan the project, so that means mission planning, designing your flight patterns, deciding where you're going to set your GCPs, flight altitude, overlap, all of that good stuff. Setting your ground control targets and checkpoints in there. You go out and you collect the data. That's both drone data and field data, obviously. A good drone program, as we'll cover more, is really a mixed workflow. It's never going to be 100% drone. It's never, and in this case, won't be 100% on the ground either. So a good drone will have your stuff on the field and stuff from the air. And then obviously we'll get into the nitty-gritty of photogrammetry, drafting Linework, and finishing it in CAD. So of these two, there's the field side of things and then the office side, and what we're talking about today is going to be the office side of things. That photogrammetry step, drafting Linework, and then finishing it in CAD. So what that means, we've got a couple of assumptions here of things that I am explicitly not going to cover, just so that you guys are aware. And if you want to learn more about this, feel free to come up and talk to me later, because we do help clients with a lot of this stuff. But it means that we assume you already have a drone. Duh. We don't really care what type of drone you have as long as you know how to fly it and can get good pictures. Which means we also assume that you can get good drone photos for a site with an appropriate camera, proper angle, good overlap, appropriate distribution, all those mission planning things that you've already kind of figured those out. But also we assume that you have good ground control points, sufficient quantity, adequate distribution. We're not going to go over what it takes to set the proper number, distribution, location of ground control points, but we will go over some of the photogrammetry tips and tricks. Well, it's hard to say. for making sure that you can check that you have enough and that your accuracy on the final survey is going to be good. And we also assume that you have done your additional ground surveying needs, things like I was mentioning, part of that mixed workflow. Things like boundaries, building corners, checkpoints, all still going to need to be surveyed on the ground. The drone is just a tool in the toolbox, not the be-all, end-all of surveying. In fact, anyone that says you can fly a drone in 15 minutes and get a total survey from that is probably overselling it. So, let's go through the office workflow now. The drone surveying journey. This is the path that we actually see most people take when they first start using drones commercially. And what it starts with is people will often buy a drone. Actually, I probably should, there's one step below that, which is buy a drone for your kid or to annoy your cat. But that's not on here. So from the drone surveying journey, people usually start with just taking basic photos and videos. Trying to get a little bit of context for the project site, showing what it's like, showing your clients what the project site looks like, having good documentation. Valuable, but not too complicated. Next up is getting ortho photos. You take those, take a whole bunch of photos, learn to fly in one of those lawnmower flight patterns, put it together. Hey, now you've got a pretty ortho photo backing. It's really good for putting context on your maps. Maybe you're going to print with it. Maybe you're going to reference a few things, make some rough measurements. Next step is actually getting high accuracy and high precision ortho photos. And that means that now you're integrating ground control points. You're actually measuring your root mean squared error of some of these projects. And you actually have confidence when you're measuring off of this ortho photo that you know, okay, statistically this is accurate to 0.15 of a foot RMSE or something along those lines. The next step is getting up into 3D data. So you start working with surface models, point clouds, and a lot of the full resolution outputs. So this is going to be a lot of the just file outputs that will come out of Pix4D or Agisoft, your raw 3D data. Problem there is it's going to be often really, really big files, really cumbersome, a lot of data that you don't need. So the next step is actually getting clean CAD drawings off of that. So how do you extract your line work? That's what we would call the line work drafting phase, where you're actually extracting your elevation points, break lines, you're coding and putting layers on all of those points and getting it into a format that you can use in CAD. Next step is actually kind of adding more culture to that, integrating it with your ground data, getting your final survey deliverables so that you actually have now a clean surface in CAD and something along those lines. And really the peak of the journey, the place where we want to get is to actually getting an integrated workflow of all of this together. So once you've done, you can get to your final survey deliverables, you can integrate your field data, your ground data, you can put it in CAD, you can add your culture, you can add your layers and symbology and blah, blah, blah. Now you need to make a good workflow for it. That means that it is repeatable, reliable, efficient, and saves, to hammer on that again, to save time and money. To save time and money over what a comparable survey would take doing it on the ground. So for us, this is just kind of a sample workflow. There are a whole bunch of different softwares that you can use. We have our favorites that I'll go through a little bit more. But there's the photogrammetry step, which the big market leaders are Pix4D, Agisoft, Photoscan. Drafting Linework, there are dozens and dozens of softwares out there. I'll talk about a few of them later today. But you can do it either in a point cloud, you can draft on the ortho photo for 2D data, you can draft in a 2.5D model with a DSM and ortho photo combo. And then of course finishing it in CAD with Civil 3D Carlson or any other of the number of suite of CAD software packages out there. But there are also some hidden steps in this. It's not just these 3 steps. To have a good, efficient, reliable drone program, you really should have QA/QC steps layered into every step of this process. Once you do your photogrammetry, you shouldn't just send it off to a drafter and assume everything works. You need to actually run your QA/QC and say, okay, Pix4D, the quality report came out with a bunch of green check marks, but is that enough? Is it actually good? If I get someone come back, am I going to be able to go to court or something and say, hey, this is accurate, and here's how I know this is accurate? So making sure that you have a good QA/QC process at multiple steps through the drone survey process will help you catch errors faster and actually save time. Because if you get to this last step, if you get to you're almost finishing in CAD, and then you discover an error that could have been caught in the first step of the photogrammetry stage, you just killed a couple of days worth of time, and that's a big problem. So those 3 major steps, photogrammetry, line work drafting, and CAD finishing, to kind of put those on this journey that we've talked about. Your basic photogrammetry will get you from photos to high precision ortho photos. Drafting kind of gets you into CAD drawing, but then really that integrated workflow is how you then work this into your existing field data. So let's talk about these at a high level and then dive into each one of them really in depth. First step, photogrammetry, stitching photos into your interim files. The outputs that we typically deal with are going to be a point cloud, orthophoto, digital surface model. There are more different outputs out here. Pix4D has a dozen different outputs, but these are going to be the primary ones that surveyors will use. They're going to be the most efficient workflow and have the most rich and accurate data. Next step, Linework drafting is actually saying, okay, we want to reduce this from that really high, rich data down to a tin, down to a surface. This is one from one of the drafting softwares that we use with just elevation points, curve lines, break lines, reducing it for CAD compatibility because the photogrammetry outputs, if anyone's ever tried to input a 10 gigabyte orthophoto into Civil 3D, you know that it's not going to happen without a heck of a lot of wrestling. And then finishing in CAD, merging your field shots, creating a surface, adding your culture and annotations, sealing it, and creating that finished survey that is indistinguishable from a conventional survey. So one more time, photos, ground control, RTK, PPK data are the inputs into the photogrammetry step. That photogrammetry creates an orthophoto, DSM, and point cloud. Then you go through the Linework drafting step, which is going to create your 3D points, polylines, typically in a DXF format, not going to be a full, rich deliverable. Go through CAD finishing to create your surface, contours, site culture, going to be a DWG format, something along those lines, and then use that to create your final deliverable. And from there, your final deliverable is, like I said, it should be to the engineer that's using it, to the end deliverable client where you print it out on a map, absolutely indistinguishable from a conventional survey. So before we dive into this, I'm going to give this next section probably not enough time because I think I want to cover some of the photogrammetry stuff in more depth. But RTK and PPK GNSS processing for drones has become a super hot topic lately with the Phantom 4 RTK's release, which is honestly a really great aircraft. It's the tripod that comes with it is terrible for whatever it's worth, but the aircraft is pretty great. So I want to talk about how we do the RTK and PPK processing for that. So surveyors are going to be familiar with the difference between RTK, PPK processing typically, but with the drone you really have three major workflow options. So you can do ground control with no airborne RTK or PPK, which is going to be the most common with the older Phantom series of drones, most DJI products prior to a year ago. It's extremely affordable. You can buy a drone for $1,000 or something and actually still get good data. Simple, very highly reliable workflow. You've already got all the equipment for high precision ground control points. Drawbacks, slightly lower accuracy than RTK, PPK, but more field time and more GCPs are required. Airborne RTK, very high accuracy, few GCPs and fewer GCPs and checkpoints, and less field time overall. Downside, it's expensive and it's a complex error-prone workflow. To be fully honest, we don't like RTK because there are a lot of things that just make it not work. From cell service trying to connect to a VRS station to a radio link that makes it drop the link to the actual aircraft. It is possible to do it, but especially with such a new technology as Airborne RTK is right now, we find it to be a very error-prone workflow. Now to be clear, that doesn't mean that the data quality is bad when it comes out of it. If you get it to work right, the data quality is perfectly fine. But getting it to work right is an error-prone workflow, and like I was saying before, this is about creating a reliable, efficient workflow that saves time and money. So we like using Airborne PPK, same accuracy as RTK, fewer GCPs, less field time. It's the most accurate workflow because you actually have a lot of options from using your own base station to using a Coors network-based base station. But it does take office time. But when you're thinking about the office time that it'll take, with drone photogrammetry, you've got to post-process it anyway because you have to run photogrammetry. So you have to take this data back into the office to process it. So why do you actually need real-time, live in the field as the drone is flying data? You don't, from our opinion at least. So this is the most reliable workflow that we've developed. So our suggested PPK, there you go. Our suggested PPK workflow is you start by gathering your data in the field. That means your actual GNSS data as well as your photos, checkpoints, ground control point. Get your correction data, run your PPK algorithms. Then the trickier part comes with adjusting your GPS data for time and gimbal offsets and integrating your data into your photogrammetry suite. And again, I'll just kind of blast through this a little quickly so that we can talk more about photogrammetry. So data in the field, photos, checkpoints. Do you still need checkpoints when running Airborne, RTK, PPK? Yes, absolutely, 100% yes. Anyone that is telling you otherwise is probably overselling their product, in my opinion, because while it is technically possible, checkpoints are extremely necessary to verify accuracy. There are too many sources of error in this workflow for you to throw a bird up in the air and just say, yeah, it's going to work, and have no method of verifying it. So you still need checkpoints, if not ground control points, to verify accuracy, calculate the amount of error in your project so that you actually know, okay, how many tenths of a feet of error am I actually seeing? Because there always is some error in the real world. The real world is messy. And also expose blunders. One of the biggest sources of error that we see with a lot of these corrections are just managing the transitions from different coordinate systems, different datums, doing grid to ground corrections, changing the vertical datum that you're using. There's a lot of source for just human in there, human error in there. So making sure that you have a handful of checkpoints so that, you know, heck, you guys are surveyors, you've seen errors from a bunch of different sources. Someone set their rod height wrong. And if you don't have some way to check that, then you could potentially be delivering bad data. So that's collecting data in the field. You do still need your checkpoints. Then you want to gather your correction data. You need your rover data, which in this case is going to be the drone itself as the rover. Base station data, you can either use CORS stations, your own base station, VRS networks even work as well. And obviously your broadcast ephemeris, your satellite navigation data. We like using NASA's. Again, when you have to post-process everything, you can wait to get the most reliable data that's out there. Running PPK correction algorithms. These are some screenshots from RTK Post, which is going to be an open source PPK correction program. You can use Trimble Business Center or any of the other PPK solutions out there as well. So usually files in, files out, just kind of know your settings. And of course, here's the tricky part is actually adjusting for offsets. When you get your raw PPK data, it's going to be typically at 1 second intervals, sometimes at 0.2 seconds if you have a good enough base station. But it's going to be location of the antenna at satellite time intervals, which is not really what you care about. What you really need is the location of the image sensor itself, the camera beneath the drone, at the time the photo was taken, which might be directly in between. So if you think the drone's flying at, you know, a couple of meters per second pretty easily, and it's at 1 second intervals, in that time it's going to be moving a couple of meters, you know, maybe as much as 5 or 10 feet in that second. So if you don't interpolate within that 1 second time interval, you're going to be introducing potentially feet of error into your project. So actually processing that for outputs and getting your required data at the time the photo was taken, the exact location of the image sensor, that's where most, in my mind, most RTK and PPK workflows up until very recently have fallen short because they still will get you a great, you know, super highly accurate location of the antenna on the drone. But with the drone kicking around, the antenna and the camera gimbal moving, the offset between the antenna and the actual image sensor center is rapidly moving and constantly moving, and being able to adjust that properly has been pretty tricky. And lastly, you need to then integrate that into your photogrammetry process. So that means managing your datums, your coordinate systems, and adding metadata to the photos so that when you do put the photos into your photogrammetry suite, that they are properly geolocated. So I know that was a whole bunch of information and that I am only kind of scratched the surface. We do have more information on RTK, PPK processing that we just give away if you want it, so feel free to talk to me or drop a card afterwards and I can hand that to you. But I want to talk now about photogrammetry, the rest of the workflow that you guys are probably more familiar with here. Photogrammetry, there are a whole bunch of options out there. Pix4D, Agisoft, PhotoScan, Drone Deploy, Carlson Photo Capture, there are a whole bunch of them out there. And you can use whatever you want. Most of these principles will apply to most of those softwares. So what is photogrammetry? It is the art and science of making measurements from photographs. So from a very high level, creating 3D data from 2D photos, and the output of this step is a rich, highly detailed 3D model. Now, as you know, rich 3D models have problems because here's some just automated contours out of Pix4D. And you can see that there are contours all around the cars and even some artifacts around the cars, which that's not what anyone wants. So it's a good interim step, but it's not quite there. There are also a lot of options for photogrammetry. There are automated services, like Drone Deploy is going to be the most popular ones. Propeller and 3DR up there as well. They're very fast and simple, but they're pretty low accuracy. To go back to that kind of drone survey journey that I was talking about, this is on the lower end where you're getting an ortho photo, but not even a super high resolution or super accurate ortho photo. Quite honestly, if you're just doing job monitoring, if you just need a photo for backing or for just very rough mapping, even for most GIS applications, these automated services are going to be the most effective method to go through. They are fast, they are cheap, they are much faster and much cheaper than buying a high-end computer, buying a Pix4D license, or outsourcing it or anything like that. So they're far and away the fastest, simplest, cheapest way to do it. You can in-house it as well. Pix4D and Photoscan are going to be two of the most popular ones. It gives you a lot of flexibility, gives you a ton of control over the process, but there's a pretty steep learning curve, which is I'm sure why a lot of you guys are here today. And it is also difficult and expensive. And expensive not just in terms of it costs a lot of money, which it does. The software can cost as much as $8 or $9 grand for a lifetime license. The computer running it can easily run up to $5,000 or more. But it's also really expensive in terms of your time. That if you as a surveyor are sitting there wrestling with a project for multiple days, that's time that you could be working on other projects. But it is good for sensitive data, unusual projects where you need that level of control, where for whatever reason you might not be able to outsource it. And then minor plug here, we're a specialized service that we do a lot of the photogrammetry drafting, Linework services for our clients as well. So we have certified photogrammetrists that have the benefit of using things like Pix4D but with a lot of experience. Slower turnaround than your automated services, but typically faster than in-house, and we think it's pretty good for high accuracy mapping. But enough sales stuff for now. Let's dive into it. So we like Pix4D, right? Is this what you guys want to see? What are some of the best settings for Pix4D? Sorry, no best settings for Pix4D. It's using Pix4D correctly and that sort of stuff. So we do use Pix4D with our company. We've got something like 8 licenses and a handful of photogrammetrists on staff. But quite frankly, it's not about get these 3 settings right and ta-da, every project that you put in is going to work. It's not about the settings, it's about the workflow. So having a standardized workflow is going to be the best thing to using Pix4D. That means you process it, maybe step 1 rapid first, and then you actually run through a set of checks to make sure that it works. And then maybe you run step 1 full again, and then you run through another set of checks to make sure that that worked, so that you catch errors earlier, faster, quicker, and better before. So having your standardized workflow, integrating checkpoints to make sure that you have some way to catch errors that aren't going to be directly on the quality report, constantly checking through errors at every step of the phase. Pix4D is a wonderful software, but it's not a black box magic thing. I mean, that's what the drone deploys of the world are. If you're hoping for a throw photos at it and ta-da, it's just going to work, it's not going to happen. You need to have a human in there looking for different errors. And we'll go through a lot of those common errors and some of the solutions for them in just a second. You need to adjust your settings based on the site. Every site is going to be different and is going to require different settings. Once you get experience, sites will occasionally require different flight settings too for how you fly it. It's from the simple things based on what altitude are you flying at to the more complex ones like what overlap and what camera angle you're going to fly at. And how do you optimize that to make sure that your Pix4D processing workflow is as smooth and easy as possible? I mentioned earlier that we kind of assume for this presentation at least that you've already flown your job site, you already have your thousands of photos. But a lot of the ease of processing is already going to be determined by the time you've flown the site. Because if you fly with bad overlap or have too much overlap, you might be making your job a lot harder in the office even before you've started any photogrammetry things. But also getting trained on photogrammetry is important. So when we say have a workflow that checks for problems, checks for errors constantly, there are 3 steps. First, you have to realize there is a problem. Seems simple, right? But it's the most commonly overlooked one, especially with photogrammetry. We love Pix4D, we love the quality report, but so often it pops up and it'll have those 5 little green check boxes next to there right at the top, and you say, hey, wonderful, 5 green check boxes, everything's okay, right? Well, not necessarily. It might be fine, but you need to go deeper than those 5 green check boxes if you're going to be putting your surveyor seal on there and saying that this is actually accurate. So first, you have to realize that there's a problem. Second, you have to figure out what caused the problem. And third, you have to know how to fix it or avoid it next time. Not every problem is actually fixable in post. A lot of them are, but a lot of them have to be caught in the office, and then you have to adjust your mission planning in the field to make sure that it doesn't happen the next time. Because really, annoying real-world things happen, unfortunately, way too frequently with this. Photogrammetry is a messy process and has errors, always. GCPs shot across multiple days can be inconsistent. We've seen GCPs set in different vertical datums, and you can fight with your photogrammetry and it'll never work because your control points are not exactly perfect relative to one another. They were maybe tied off of two slightly different benchmarks, and like I said, someone said the rod height may be wrong. We see that happen all the time. The camera can physically or imperceptibly be knocked out of calibration. A GCP target can be moved. And all of this sort of stuff will cause errors that literally, hell, you can actually wrestle with the settings in Pix4D sometimes to hide errors. Sometimes you're going to see errors in Pix4D, and it's because of an error in the field. We've seen all of these problems happen a lot. Rod height puts the whole project on a slope. Someone comes and kicks a ground control point between when it was shot and when it was flown, and no level of processing or automated processing is going to fix that problem. As a photogrammetrist, it's your job to actually know that these types of things can happen and be able to identify them. So let's talk about our best ways to identify errors. There are typically three main tools that we use for identifying errors. The first is analyzing the quality report. We will be using Pix4Ds for some of these examples. The next is using check shots. You've heard me talk about that before. That's really important throughout the whole survey process. And honestly, if you're out in the field and you've got your survey equipment, use check shots anyway. It takes another couple of seconds to just shoot a few extra points to validate the accuracy. And last is gaining experience with photogrammetry. A trained eye can typically spot some of these problems very quickly. So I'll give you some resources for how to get better trained in photogrammetry. So let's talk about our quality report here. Just because everything is green doesn't mean your data is good. So what I have here are three different sections from an actual Pix4D quality report from an actual project that we've done. And all of this is live data from the project. So if I look up here in the top right and I say, okay, we've got our main checkpoints. How many key points per image? Green check, great. 449 out of 451 images calibrated, all enabled, great, that looks good. Those 2 ones are probably snap test photos on the ground, so they didn't calibrate, no big deal. 0% relative difference in camera parameters, great, that means my initial camera parameters were somewhat close to the default ones. Doesn't necessarily mean that it calibrated correctly. Matches per image, good, and GCPs with 8 ground control seems pretty good for 450 photos, probably right about the right number, with a mean RMS error of 3/1000ths of a survey foot. Now, does this mean that the accuracy of this project is 3/1000ths of a foot? Yeah, right, because the data says it, so we can trust it. It's a green check and it says 3/1000ths of a foot. Man, I'm such a good surveyor. You suckers out here only measure into a few tenths or something, and I can get 3/1000ths. No, it is obviously not the case. Ground control points, the program is calibrated to the ground control points. That number will always, in every single scenario, be better, way better than the actual measured survey accuracy. I think one of the most misleading things that the Pix4D quality group does is put that green checkbox and that RMS error up there right on the top for everyone to look at. That is not an accuracy number. That checkbox being green does not mean that your survey accuracy is good. If it's red, it does mean that there is an error, but if it's green, it doesn't mean that everything is perfectly clear. So let's look a little bit more at this project. We have our individual ground control points there on the bottom right. Those actually look good, but it's important to look at your individual ground control points as well to see not just what that top level RMS error is, but to see what kind of the spread is. Not all ground control point errors are going to be normally distributed. Sometimes, not in this case for this project, but sometimes you might have 10 ground control points that are good and one that's off by 3/10 of a foot. That would be a huge red flag for me and my photogrammetrists as well. Looking around and saying, okay, you do the math, our RMS is still pretty good, our RMS is still less than 1/10 of a foot, but why is that one check shot off by 3/10? That's out of tolerance for us, even though that green checkbox says all is good there. And that could be a bunch of different things. It could be it was kicked on the ground. It could be that it was out of spec, so an area of high altitude where you didn't have good overlap or something like that. But it is important to check all of your individual checkpoints. That's one of the next major steps that we go through is checking those individual control points. Sorry, not checkpoints in this case. These are control points. And then lastly, I covered the matching map, or put the matching map on this project up here as well. Because this is a project that, like I said, if you really just kind of glance through it pretty quickly, all the data looks green and all the data looks good. But if you look at that map, we can obviously see some problems. I mean, over here, it's obvious that this data, there's plenty of photo matches between photos, but over here we actually have really poor matching. And in some cases, we have some photos that actually look right here like they're just standing off by themselves. They might not even have calibrated perfectly into the model. So what probably caused that? And this is one of those things that comes from experience looking at this. I can look at just this photo match report, and I don't even know exactly what the ground looked like on this project, but I can tell you with a high likelihood that the elevation increased there. And that means that the elevation increased, the drone was flying at a fixed altitude, the amount of overlap at that level went down. That's probably what happened. It could have been vegetation as well, but I would guess elevation from looking at this one. And so when I read this, what this means to me is that the accuracy on the right-hand 2/3 of the project is actually going to be pretty good. I need to see what the resolution is, the sampling distance, flight altitude, blah, 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 but I'd say that the accuracy, at least X and Y on that right-hand 2/3 is going to be probably around 1 or 2/10 of a foot. But on the left side of that project, that's unreliable data. Pix4D is still going to put out a point cloud there. It's still going to put out a digital surface model where it'll have a surface, and it might even be kind of close to what you actually want it to be. But that's going to be unreliable data in that section. So you need to know when you're doing these sorts of projects, when you're analyzing your data quality report, that, okay, if the main area of your project site what you care about is on the right, great, no problem. Push it through to the next step, past QA, and you're good to go. But if what you care about is that left-hand side, then you need to revisit this, possibly reprocess it, possibly add some manual tie points, and possibly just throw out some of that data and go back and shoot a little bit in the field to fill it back in. All right. So I'm happy to answer any questions too if anyone has questions on the quality report or some of the stuff we're going through today. But moving on, the next way to check for errors are having those checkpoints. Our best clients, the ones that use us most frequently, will always have a handful of checkpoints that should be independently measured and must not be used in photogrammetry. If you use them in the photogrammetry process, they are not checkpoints. They need to be independent because otherwise you can wrestle with your settings to get it to fit the checkpoints. If you wrestle with your settings to get them to fit the checkpoints, then you don't actually know that the data within that isn't a checkpoint is going to be good. The checkpoints need to be independent, and they shouldn't be evenly distributed. We see a lot of kind of abusive checkpoints too, where people take maybe one checkpoint and then they'll process Pix4D, and they'll say, oh, the checkpoint was off by 4/10, and then they'll change their camera settings a little bit. There we go, that one checkpoint's now at 3/1000ths of a foot again, so we're perfect, right? Well, no, you just kind of manipulated the data to the checkpoints. They should be independent, and they should really be used to measure accuracy, not to create accuracy. Checkpoints tell you what your accuracy is, and don't let you really improve it, because at that point, again, they're just ground control points. They're not independent. And then the last way, like we said, is getting experience with photogrammetry. The best way to do that, for those that aren't aware, ASPRS is a nonprofit organization that's been around for a shockingly long amount of time for aerial surveying data. Founded in '34, nonprofit. They have all kinds of educational resources and certification programs. There's my certified mapping scientist certificate up there. I'm kind of proud of it. It's specifically the UAS certificate they recently started offering, and I got number 2. I don't know who number 1 is yet. I'm still trying to track that down. So if anyone knows who it is, please let me know. But becoming a photogrammetrist takes a lot of time. And there are a lot of the errors, kind of like these ones that I'm seeing, that you learn from experience. So being able to have those resources available to you to learn what some of the different possible errors are, to learn how to correct for them. I'll go through as many as I possibly can today, but there are going to be still more that honestly just take years of experience and practice. And that's the organization that we definitely recommend is pretty good at teaching stuff.
Yeah. Hey, so on your verification on the GCPs in Pix4D, I saw some of those that had 13, some of them had 7, some of them had 4 I mean, what's your rule of thumb on the GCP verification?
Great
per
question.
image?
To me, every single project is different. And it totally depends on your specs for the project. Sometimes if we're doing a couple hundred acres and all you need is 1 foot or maybe 2 or 5 foot contours even, if I see a handful of control points that are off by 1/10, no problem, right? Because for that project, if you flew at super high altitude and you're getting 1/10 of variance, and heck, maybe we throw in some checkpoints and we even see 2 or 3/10 vertical variance on a lot of the checkpoints, that's within spec. If you're doing just real rough 1 foot contour mapping over a large area. Now, if you're doing an as-built survey on a gas station and it's all hardscape, and I saw 1/10 of a foot vertical error there, that's going to raise a huge, huge, huge red flag for me. So you really have to look at it within the context of the project that you're doing and what the required accuracy is. The other
He was
thing,
asking about the number of pictures that were verified.
oh, number of pictures verified as well. Yeah, that matters in the sense that, so rule of thumb, I like to see no fewer than 6 on the low ones. If you fly at what we recommend a good middle ground overlap is, which is 75-75 for a single flight pattern, that to us is a very good balance between efficiency in processing and very good quality data. Any less than that, you get lower quality data. Any more than that, you typically wind up with way, way, way longer flight times and no increase in data quality. But 75-75 means that a lot, you'll see somewhere between 10 to 6 or 9 to 16 photos per point on the ground. Just talking about that real quick, because I know that's part of the mission planning that I wasn't going to talk about too much, but overlap overkill is a real problem with photogrammetry when it comes to creating an efficient workflow. Pix4D will often encourage you, take more photos, throw more photos at it, but that's because they assume that super high-end computers are free, which they're not. They assume that time happens instantaneously, which it does not, and that your time as a surveyor is free, which it's not. So making choices in the field to make your data processing life easier is pretty important. In fact, that's what I'm going into next, is managing processing time. So like I said, much of your processing time in Pix4D is actually going to be decided in the field with your mission planning. There is such a thing as too much data. Overlap overkill, that's what I was just talking about. You can fly at one of those crosshatch flight patterns where you fly north and south with an 80% overlap, and then you fly again east and west with an 80% overlap. And your data is going to be great, but it's actually, we've done a lot of tests on this, it's not going to be better than on like a just topo survey, it's not going to be better than a single 75-75 flight pattern. There are some edge cases, sure, where it will make a difference if you're mapping the facades of buildings, but it's going to just kill your processing time. Flying too low is another thing that we often see. People think lower, better quality photos means more accuracy, right? Well, yeah, but it also means you're going to have to set more ground control points to get that accuracy, and it also means you're going to spend a lot more time in the field. It means you're going to spend a lot more time processing the data, and your files are going to be a heck of a lot bigger and more cumbersome. So don't fly too low if you don't need, that super, super high accuracy data. Sometimes you absolutely do. To go back to that other example, if you're doing an as-built survey on a half-acre plot and it's all hardscape, oh yeah, slam that thing as low as you can. 100-foot flight altitude, fly it with reasonably high overlap, and you're great, because at a half-acre site or something, it's never going to be more than 100 photos. If you are doing a 20-acre subdivision topo and all you need is those 1-foot contours, don't fly it at 100 feet. That's ridiculous. And partly because processing time with photogrammetry is not a linear process. 100 photos takes an hour to process maybe, 200 photos doesn't take 2 hours, it takes 4. Usually you 2x the photos, you 4x the processing time. And for anyone that's done this, you say, oh, well, I have this photo, it's 1,000 project that's 1,000 photos, then you do another one and it's 2,000 photos, and all of a sudden, your computer's cooking for 3 days. And most people have this knee-jerk reaction of, well, it's taking my computer so long to process, I need a better computer. I need to buy a faster computer, right? Throw more money at the problem. Get the latest Intel i9, fluid-cooled, server-grade, whatever. It's only, hey boss, it's only 15 grand for this latest server. It's pretty bitchin', right? But honestly, a good workflow is worth much, much, much more than a good computer. Having a good field workflow to know when you can cut the amount of flight lines that you take will save you so much time in the field. Having a good office workflow so that you know, heck, if you get too much overlap, you can throw out some of the photos. And in fact, we often do. One thing that we see a lot from our new clients is they'll test the program and poke at it and say like, hey, so we flew one job site with what you recommended, 75% overlap, but then we wanted to see if it was better accuracy, so we flew it at 90% overlap. Which 90% overlap, if you kind of do the math, that means each single point on the ground will be visible from 100 photos. Not 16, 100, because it gets multiplied and squared and whatnot. And you give them a call, it's like, what are you trying to do here? It's gonna take you a week to get this data back. It took you so long to fly this. Like, the data's not gonna look any different. And even then, because photogrammetry is this weird process, just because it happens in one project doesn't mean it's gonna be a repetitive thing in every single project. There are so many variables in this, including the real world. It's messy. But ultimately, one of the things to manage your processing time that we think a lot about is always stage your processing. Run step one multiple times if we're talking in Pix4D. Don't just blindly throw all 3 steps on your computer every single time, because that way, when you discover an error, and you will discover errors constantly, that is not a sign of you being a bad photogrammetrist or a bad surveyor. Quite the contrary. It's a sign of you being a good surveyor because you're catching these errors. You will catch errors. That is part of the normal course of photogrammetry. It is not from bad flight planning. Sometimes it is because of just weird aberrations. Sometimes it's because a bug landed on the camera lens and introduced some level of vibration to it. Sometimes it's because the camera actually got knocked slightly out of calibration just from being thrown into a truck or something, and the camera parameters changed slightly from the last time you processed this. So run step one multiple times, stage your processing. Our recommended workflow, at least in photogrammetry, run step one rapid, integrate your ground control points, run it again to make sure that they broadly check out, then run it again on step one on full, and only then, once those check out, do we even consider throwing it into a full processing queue where we actually generate a full resolution point cloud and a full resolution ortho photo, because those are going to be some of the most processor intensive steps for that sort of thing. So, any questions about processing time or some of this stuff? Let's keep going. Let me show you some of the sample problems that we actually see. Here's where a lot of, when we talk about that workflow of checking for errors, here are a lot of very common errors that we see in photogrammetry projects. All right, number one, features can split projects in photogrammetry. So we've got this project site right up here. They were going to fly it at a pretty high altitude, 5 ground control points. Typically that's going to be sufficient for a project like this. But this one's pretty bad. If we see this, I would know before processing it, or honestly, heck, even in the mission planning process, that this is not going to work. Because water is impossible to stitch together in photogrammetry. So what that big river does is it actually splits the project into 2 different chunks. And you have 3 ground control points on that left-hand side and only 2 on the right. And 2 is certainly not enough, because you've got that thing floating. It's not even tied down in triangulation. 3 is geometrically speaking enough, but from a real-world perspective, no, it's not enough ground control points for a project. And here's the most insidious part about this project as well. The Pix4D quality report would probably come back and show all green processed into a single block, because you have that tiny little spit of land on the north that's connecting it. So you have one photo that's going to connect those 2 blocks, and then the other ones are just kind of like free floating out there. But the 5 ground control points, well, hey, they'll check out 0.003 of a foot accuracy. Green checkbox, good to go. Even when you check that, even when you check the individual ground control points, you'll see, yep, they're all in a lot of photos. There's going to be plenty of overlap, no aberrations there. But to go back to this chart right here, where'd it go? There it is. This chart right here, you're going to see a big on one of those. And that means you need to be really, really careful, because the data quality is probably going to be bad on this project unless you have more ground control points. Now, this is a project where the solution, when you see something like this, if you're already in the office, there's really not much you can do for it just in the office without going back into the field. You might have some additional checkpoints. If you have some additional checkpoints or field data shots along the bank of the river or somewhere out there, then you can add visual ID points in and that would help solve it. Or potentially you need to send a crew back out to take a few supplemental shots to make sure that this is good accuracy. But that's that's like an example of one of those projects that you need to be aware of. And it can especially happen with novice pilots that just hear the rule of thumb, 5 ground control points, flyer job site, bing, bang, boom. It'll take them time to learn that, yeah, this is not going to be enough for this project. And as we're talking about multiple blocks is another big problem with Pix4D and photogrammetry, because a lot of things can cause multiple blocks, the project to process into multiple blocks. Some of it's based on site conditions. In this case, what we're seeing is this was actually the area of interest down in the bottom of the screen, and then the top was another area, but in between it there was some really dense vegetation, some forests and trees that the client didn't really particularly care about, so no issue that there was nothing there. But if there were, again, only 5 ground control points on this whole project, then that's not going to be good. That's not going to anchor everything together. You need 5 ground control points per block, per calibrated block, to keep those things tied down. So be aware when you're looking at those, or even when you're doing that mission planning, of what can separate a project. So whether it be water or dense forests are typically going to be the common causes for projects separating into multiple blocks. But honestly, even uniform grassy fields, any sort of agricultural fields are in there, sometimes those can cause a project to break up into multiple blocks, which can be fixed by adding manual tie points in those cases. But it's just something to be very, very cognizant of, that multiple blocks, insufficient ground control points is very, very bad and a very dangerous thing. Moving on to another example, artifacts. Artifacts happen in photogrammetry. Smooth surfaces are especially subject to this. So things like very, very fine uniform sand, very fine uniform freshly poured asphalt or water, like I said, will cause artifacts like you see here on the right. Now this example is probably a bit more exaggerated than a lot of the artifacts that you'd see, but it's the same basic principle. Now is this a problem? I actually say no, it's not a problem. It's something you need to be aware of, but it's one of the just like mathematical in principle limitations of photogrammetry, that perfectly uniform surfaces are not going to be able to be matched and create an accurate surface on them. Now, what a good photogrammetrist would do, or actually what a good Linework drafting technician would do on this, is they would be able to identify these artifacts even after the Pix4D stage, and then only pick out the points that are good. This one, like I said, is an exaggerated version of it, so it's probably not that good of an example, but usually when this happens, the asphalt will have all these weird, crazy spikes and divots and whatnot, but there will be a couple oil slicks on the ground where the photogrammetry software was able to create a match, and that's going to be a good point. There will be the paint striping where the photogrammetry was able to create a proper match, and those are going to be good points too. So a good Linework tech can actually identify the points within the noise and say, yep, there is a bunch of noise and artifacts, but here are good points, and we can create a clean, good, accurate, reliable topo surface off of that. How do you check all this? Checkpoints, experience, looking at it, QA/QC processes. The same things that I was saying earlier are how you identify these and say move forward. So what we say is reduce these things where possible, but adjust the workflow where not. You can make some settings to slightly reduce this sort of noise in Pix4D. You can up the number of matches that are required in individual photos in step 1. You can up the number of matches in step 2 when actually creating the point cloud. Or you can go in and manually edit the point cloud after step 2 is run before you're generating your DEM and ortho photo and blah, blah, blah. We generally don't like that. It works, but it's one of the very, very time-consuming processes that are out there. We like to manage this and adjust the workflow for this type of error in the Linework drafting stage. So next up, just kind of some more errors to talk about. This is another one that shows where there was horribly insufficient overlap for a project, and yet your Pix4D quality report is going to come out and say everything's all hunky-dory again. Because technically, this is all going to process into one block, but you see there are a couple of those kind of green circled areas on the left that are going to be really, really bad overlap, just a single flight line. And all of a sudden, you start getting this kind of twisty project that with only one ground control point in each of those sections. So it is going to process into one block. It is going to have 8, 10 ground control points or something, but the data on this, absolutely unreliable. It may look reliable. Everything in the quality report may look reliable on this one, but I wouldn't trust it. You're going to need some extra checkpoints, extra ground control points to be able to do a project like this. And yeah, this is something that you should be able to spot as part of just a regular QA/QC process. Some other just funny ones that we've seen GCP targets get kicked and cleaned up. This is a one of our real projects where we had a target and a landscaping crew that thought that our ground control point was trash. So you can actually see the little yellow back of the ground control point in the truck on the right-hand side. Yeah, so that was a huge pain. This was a big project for us. And this was one of the corner ground control points too, so it was actually pretty critical that we had that one right. So what's the solution? Well, we went back out and we just shot that corner. The rest of the project was still good. We had enough ground control points, so even though we lost that one, we were fine. But these sorts of things happen. And again, like there's literally nothing you can do in post to fix this. This is one of those errors where you need to identify it, and it's not going to be in the quality report, but you need to identify it. But there's no magic setting. There's no magic, oh, well, if you set your camera calibration parameters to X, Y, Z, and if you make sure to estimate from XIF when you're doing your distortions. Like, no, that doesn't fix an error like this. These errors just happen in the real world, and they're no one's fault. Well, it's kind of that guy's fault. But it's not your guys' fault that these sorts of things happen. The real world happens. I mean, I'm sure you've had your own tripods kicked or someone just messed with the project before, and yeah, it sucks. But the best way to do is have a workflow that is resilient to handle it and understanding what you can do when something like this happens. A few other examples is insufficient ground control points. This project, single block, weird flight pattern. I don't know why they did the double crosshatch. But there's 6 ground control points all around the edges. Really, this one's going to need a ground control point in the middle for good GCP geometry here. One of the errors that you would see in a project like this is something that's often referred to as doming, where the camera calibration adds a little bit of distortion to the photos, that you actually create like a big dome or sometimes a valley when you only have GCPs on the outer edge of a project. That's especially common with older drones as cameras get knocked ever so slightly out of calibration. And when I say out of calibration, I mean like 1 or 2 pixels out of calibration, absolutely imperceptible to the human eye. But this is a project where we would definitely want to see a control point in the middle, or at the very least checkpoints in the middle to make sure that doming isn't happening. So this is such a weird flight pattern, I should point out. I would almost want to throw out probably half of those photos in the photogrammetry processing. They're just unnecessary, increased processing time. They aren't going to hurt. It's not going to hurt your accuracy, but it hurts your bottom line, and it hurts your turnaround times. And that's almost more important. Another common thing that we see, bad targets. Bad targets are a source of error in a lot of this. So this looks like a reasonably good ground control point. Someone just took a piece of paper, but finding the exact center of that piece of paper can be tricky. It might be not too bad, but maybe you're only off by 1 or 2 tenths, but especially when you start trying to identify the center of that from multiple angles, it starts to get pretty hairy and add maybe just a tenth, maybe 2 tenths of error into the project. Different corners of concrete too, those we actually don't like. Curbs, anything on a sharp edge like a curb is going to be a bad ground control point. These ones are tricky because they also make whoever's doing the photogrammetry, if they're not the same person that's in the field, it can make their lives hell. Because if you say corner of concrete, you don't know if it's, when you're marking the ground control point for the first time, you don't know if it's that corner or if it's the corner that's a couple of feet just so that can just add confusion to the workflow. Clearly marked targets save you a lot of time in the marking, GCP marking phase as well. Chevrons are kind of annoying for us. I don't know how this is non-standardized, but we have seen surveyors mark the outside tip of chevrons, the inside tip of chevrons, or the distance in the middle between both the outside and inside of a chevron. I don't understand how there's so much inconsistency for how to mark a chevron. But that is another just like introducing a source of error. And I should point out, I think the favorite project that I've ever seen. Yeah, is it a headshot or a body shot? What do you do? Come on. So generally, we don't recommend those. Again, they just add little bits of inaccuracy to a project. They're not going to be the difference between a good project and then all of a sudden you're 10 feet off, but they add error and that compounds. So we like to just your standard kind of checkerboard tile pattern, something like that. Cheap, reliable, easy. That's the best way to set a ground control point. Makes your photogrammetrist's life easier too because it's very obvious from the air which one it is. So If you have one guy flying it and shooting it in the field, another guy processing it, that makes it doubly important to use clear, obvious ground control points. There are also going to be a lot of different types of errors that you may not ever realize happens. GCP distribution can cause inaccuracy. You want to pick that up with experience and checkpoints. GPS errors in the measurement of ground control points, whether it's GPS multipathing, rod height errors, multiple crews running off of slightly different benchmarks that they've tied into, random blurry or unfocused photos, we've seen that happen before, subtle camera calibration inconsistencies. Again, real world is messy, it can cause errors. What I have here is an example of what can happen when an image sensor occasionally gets knocked off balance. If you imagine this little checkerboard pattern is actually the image sensor itself that's glued on the inside of the camera lens for your drone. And this is the field, we get it, these things get moved around. Even if you totally baby it, it's going to kick around in the wind and whatnot. Over time, they can shift very imperceptibly. 1 pixel, 2 pixels maybe, totally invisible to the human eye. But as that camera calibration gets knocked ever so slightly out of whack, that starts introducing error into your project that can only be discovered with checkpoints typically. So be aware of those errors and have that workflow in place that can catch the errors, and catch them soon. Catch them in step 1 rapid. Don't catch them after 3 days of processing on a $15,000 rig or something like that. Because ultimately all of this error compounds. Ground control, placement, distribution, targets, your camera, your mission plan, your overlap, high relief sites, blah, blah, blah. All of these errors compound. So ultimately, to kind of wrap things up a little bit on the photogrammetry side of things, our general recommendation here, photogrammetry is hard. This is really hard. I wish I were a good enough teacher that I could say, hey, after this 2-hour class, you're going to be a certified photogrammetrist. But that's not the way it works. Pix4D is a wonderful software, we like it, but it does have a learning curve. It's very easy to learn and very hard to master. When I say we find errors in nearly half of our clients' project, errors don't even mean often that you do have to go back into the field or change things. It means that, we ran through our QA/QC process and something failed. Let's take a look at it. Well, yeah, we need to tweak the camera calibration a little bit. We need to add a couple manual tie points here. We need to change the settings to see that this process is in one block. And we need to maybe throw out 5, 10, 15 photos on one of the sides that are causing a separate block error. And then we reprocess it, and ta-da, everything works out. So finding an error is not even necessarily a bad thing. It's part of the process of finding and then eliminating those errors. Camera calibration is common. Ground cover, lighting conditions errors. There are projects out there where you fly it and it's sunny at the start, and then the clouds come over and it's cloudy for the other half. Sometimes that can process fine. Sometimes that can make, again, that kind of forked multiple block project. Just something to be aware of. Another of many things that you can be aware of that typically can be fixed with a handful of manual tie points or something too, even if there is an error. Knowing your ground control settings. Our rule of thumb, 5 ground control points per flight battery or so, unless you're using RTK, in which case you can get away with a lot fewer. And even knowing and managing your coordinate systems too. Pix4D is better than a lot of the other softwares at managing coordinate systems, especially because you can do arbitrary local coordinate systems. But if you have to do grid to ground conversions, it gets really messy. If you're working in anything other than the standard EGM ellipsoid, then Pix4D gets really messy because they don't support NAVD88 or anything like that. And ultimately, there's a reason that photogrammetrists are called scientists, because it does take a lot of experience. I'll put in another plug for the ASPRS because we think it's a really good organization. You can get certified there. They have different experience and testing requirements too if you want to get certified. But we really recommend that for whoever's doing your photogrammetry, have someone that actually has some sort of training and certification in photogrammetry. Pix4D offers their own certifications. Those are pretty entry level because they want to enable as many people as possible to just be able to use it. And honestly, it's great. Like I said, if what you need is low accuracy mapping, yeah, use all your default settings, throw it at the software, and once you get back, it's going to be pretty good. But it's not going to be 1/10 of a foot reliable to the point where you could use it as an exhibit in court good. And that's what we want to get to as part of our workflow. All right. So,
I have
yeah,
a question on that
please.
ASPRS. What resources do you recommend as far as specifically if they have training classes that do they offer? Are they books? What's the...
They have training classes and workshops that they offer a lot. They have an annual conference. They offer some workshops typically at some of the major drone conferences, Commercial UAV Expo, Interdrone, things like that.
What's the track as far as working towards getting the certified scientist?
Step one, visit their website. If you drop me your card, I'm more than happy to send you a lot of the requirements. Typically, they have a couple different tiers. They start at the technologist tier, which requires 3 years of photogrammetry or related experience. It's like getting a lot of your survey designations. It doesn't have to be 3 years working in drones. And then the scientist level takes 6 years of experience. Obviously, the drone surveying industry didn't really exist 6 years ago, so that's kind of a little bit of a catch-22. But if you've been working in survey for long enough, and then you've been working with the drone for a couple of years, and have actually overseen the management of projects, then that really helps. They also have textbooks as well that they sell. I don't love their textbooks. They're very academic, very dense, sciencey textbooks that are great for studying for their exams, their certification exams. But they carry a lot of that kind of academic, mathematical side of photogrammetry. Photogrammetry as a process is interesting. The basic principles have been around for, hundreds of years for ground-based photogrammetry and almost 100 years for actual aerial photogrammetry. It was actually used in World War I, I found out not too long ago, the basic principles to try and create basic topo maps of enemy battlefields. And the basic principles have stayed the same. Triangulating multiple points on the ground from photos taken at different locations, but the way that it works is just different. So that's why ASPRS is so great that they've been doing this for 100 years. And in fact, the next thing I'm going to talk about is measuring and reporting accuracy with this. This is a really good step for your workflow. Like I said, you should measure and report accuracy because 0.003 of a foot is not real. But the principles behind how you measure and report accuracy are really, really well tested academically because this has been done forever. The technology used was way different. We were using big, large format analog cameras, sticking them in a stereo plotter, and drafting off of that. And now we have thousands of photos, not 2 big glass negatives. And instead of creating just a handful of points, we're creating 100 million points in a point cloud. So the technology's there, the fundamentals are there, the academic research and everything backing it up is totally sound. But and that's what gives us these ASPRS positional accuracy standards. So these are published by the ASPRS, American Society for Photogrammetry and Remote Sensing. They were published in 2014, and they are used to measure accuracy for aerial data. One thing that is great about these, they are sensor agnostic. They do not care if you are flying aerial LiDAR or aerial photogrammetry or even thermal or infrared or something like that. They do not care if it comes from a drone at 100 feet, a drone at 400 feet, an airplane at 3,000, 30,000, 60,000, or even satellite imagery can actually be used for these as well. But what they do is these positional accuracy standards are a set of best practices for how to accurately measure data. They do not specify how to get good data. That's on you. But what they can do is they can tell you, all right, you've done all of your work, but we'll tell you what your accuracy is. Like I said, these have been developed. The academic base for these standards is decades old. So that's why we like them. They're really reliable. They're very well proven out. And they're future-proof too. Even as drone technology changes, by being sensor agnostic, you can verify your accuracy pretty easily. So when we talk accuracy spec, let's talk about that for a sec. This is a rough chart that we kind of put together for some best-ish practices and expectations for what accuracy you can expect at different flight altitudes with different quantities of ground control. Now, this chart is optimized for a Phantom 4 Pro or a Mavic 2 Pro as well, because that has similar camera specs. Different drones, you have a higher quality image sensor or a lower quality image sensor. It'll slightly tweak these numbers, but the rule of thumb is pretty much the same. Now, we see a couple of things in here that are pretty intuitive, right? When you fly low, you can cover less ground. with each battery. So each one of these is a single battery. So 100-foot flight, you can cover about 5 acres. 400-foot flight, you can cover about 50 acres. Actually, it's a little bit more than that, but whatever, close enough. Expected accuracy, the lower it is, the better possible expected accuracy. But now that ground control thing, that's where things start to get really tricky. Because at 100 feet, you need 5 targets per 5 acres. At 400 feet, you need 5 targets per 50 acres. Now what were to happen if you were to fly that 50-acre site at 100 feet? Well, all of a sudden, you'd need 10 flight batteries. That would be a pain. That would take a ton of time in the field. And obviously, you need to buy all of those batteries, which are expensive. And instead of 5 targets, you'd need 50. If you only set your 5 targets and flew 50 acres at 100 feet, the accuracy between those points is going to be terrible. Way worse than that 0.4 of a foot vertical. Those are pretty conservative numbers, by the way. Usually we see better than those 0.4 at 400 feet. But they're pretty conservative just in the way that we like to report our accuracy. But if you fly and only set 5 targets for 50 acres at 100 feet, then you're going to see a couple feet of vertical error in between there. So this is what our kind of estimate is, though, for the accuracy that you can expect. But let's talk more about when we say accuracy, what do we mean? Accuracy has a lot of different, people have different definitions of accuracy. A lot of surveyors, especially with vertical stuff, will use national map accuracy standards. They were the standard for a long time of making sure that, I forget exactly the numbers, I think 90% of check shots have to be within a half foot contour interval. Some people will just say, yep, I shot 3 extra points and the worst one was only 600ths off, so we're good there. But I think it's important for the industry at some point to really coalesce around what a good definition of accuracy is. And for us, we'll lean on those ASPRS positional accuracy standards, which is root mean squared error. It's a statistical measure of what the actual average error is for a project. And what that leads you to is ASPRS accuracy classes that have very clear settings of, okay, you must measure 20 checkpoints in order to certify a project. You can actually use ASPRS as their own language for reporting accuracy. And say it was tested to meet this accuracy at this standard, and we have determined it's got an accuracy class of 1.25 centimeters, or 2.5 centimeters, or 1/10 of a foot. And it has this table over here for what those horizontal accuracy classes are. They do mandate, in order to report and verify accuracy, that you use checkpoints, not GCPs. Once again, I'll go back to that quality report I brought up. 0.003 of a foot is a comically unrealistic accuracy number. In fact, I've learned that there's so many drone providers out there that honestly doctor their data on the quality report and checkpoint that they just kind of extract points from Pix4D and then flip them over to checkpoints and say, ta-da, look, my accuracy is 200ths. 200ths of a foot on checkpoints. Well, that's stupid. Anyone that knows that, 200ths of a foot, and they said they measured those checkpoints with like a VRS, like a Trimble Catalyst GPS system. It's like, what? You're not getting 200ths of a foot on your ground measurement. So to say that you have 200ths of a foot accuracy on your actual drone survey is just a joke. But you need to use checkpoints, independent source of higher accuracy. Understand that there is error inherent in your guys' system as well too. That's just well known. GPS has its own levels of error. Total stations are better but not perfect. There's always error in the real world. And to meet the full standards, to actually be able to certify the accuracy of a project, you want a minimum of 20 checkpoints, is what the standards say. Now, reporting it, this is what the language from the ASPRS positional accuracy standards looks like for actually reporting accuracy. It says this data set was tested to meet ASPRS positional accuracy standards, blah, 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 for a XYZ centimeter root mean squared error horizontal and XYZ centimeters for vertical, which equals X at a 95% confidence level. Big kind of mouthful of language, but the fact is this is the type of thing that absolutely can, will, and does hold up in court. And it says, yes, I verified, I know my accuracy, I know the limits of my equipment, and I know what I am doing. If you want, I'm more than happy to email anyone a copy of these ASPRS positional accuracy standards. It's a little bit of a dense read. It's like 30 pages of heavy academia, if you're into that sort of thing. But it also has some really, really good best practices for how to set your ground control points. If you ever utilize LiDAR data as well, there's a lot of information about LiDAR and LiDAR accuracy verification in here as well. All right, any questions on verifying accuracy? Cool. Let's move on to the next stage. So let's say that we're done with photogrammetry. Hooray! Now instead of thousands of photos, and let's say we've got all of our check shots done, all of our workflows great, it's only taken us a day because we're pros at this. You now have a 15 gigabyte point cloud. Good for you. What do you do with a 15 gigabyte point cloud? Well, the next step is Linework drafting. So what is Linework drafting? I kind of showed this before. It is reducing that rich model into a CAD-friendly surface because CAD does not like 15 gigabyte files. Photogrammetry outputs are too big for CAD. Both the point clouds, the ortho photos, the DEMs, even if you try and fiddle with the stuff in Pix4D to reduce those outputs, you're going to be losing a lot of resolution, losing a lot of fidelity to those files, and typically you're still not going to make it work super smoothly in a CAD program. So why is it necessary? Files are too big, too much data you don't need, not enough data that you do need, or ugly data, bad contours. Talked about this before. This is what the rich 3D model looks like. You have those really jaggedy contours that are going around every rock and pebble. You have your actual kind of trucks, cars, whatever, but also things that I'm sure you're aware of, plants, artifacts that I was talking about. All that's going to be in the rich 3D model that you don't care about. So you want to draft it and extract the elevation or the individual points. Now there are generally what we say there are 3 different options, just like there are options for photogrammetry, there are options for drafting as well from an operational standpoint. And I'll go into the individual softwares in a second. But first, there are a lot of automated software analyses out there, and a lot of ones that are saying, hey, upload a point cloud and ta-da, we'll do automatic point cloud classification, we'll say which points are which, we'll clean the data, we'll do this, that, and the other thing, and it'll be wonderful. Realistically, in our experience, these methods are not there yet. It's going to take a while. With advances in machine learning, AI, that sort of stuff, sure, it's absolutely possible that this is going to turn a corner at some point. But right now, these automated software analyses of the rich data that try and automatically draft line work require staggeringly enormous amounts of QA and QC to the point where you might as well draft it yourself. Or use tools to draft some of it automated in an automated manner and still have a lot of human oversight and human intervention. I always say one example that's really, really tough for an automated program to do is if you're surveying a site and there's a big pile of debris in the middle of that site, do you include it in your survey? Well, it really depends on who the survey's for. If you're doing it for a waste management removal company and they need to know how many dump trucks they need to remove that debris, then yes, that is the critical part of the entire survey. If you're doing it for someone that's looking to scrape all of that off and know how much dirt they have to move around to change for an earth moving project, then yeah, you exclude it from the survey. It's a human judgment call. It totally depends. What are you actually doing? Or sometimes what the right answer might be is actually have the right classification so that when you give it to an engineer, they can turn on and off the debris piles, no problem, and have multiple surfaces on there. So this is why automated analysis, it's just not there yet, in our opinion. Something that we keep a close eye on because we think it's going to get there, and we're excited about the opportunities that automated software analysis can get to. But it's not quite there yet. Another option is then in-house drafting. Very high accuracy, reliable, known product. You can use the software. You have all kinds of control over the entire process. But it's going to be expensive labor. Typically, if you guys as the actual surveyors are there doing just very basic visualization, digitization work, click, 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 drawing points, that's not going to be the most efficient use of your time, especially if you are a licensed surveyor or a trained photogrammetrist. Yeah?
Have you worked with pixel classification?
Pixel classification?
Yeah.
Oh, is that an individual software? Or?
No. Where you're able to determine what the veg type is or what the feature is based off of the color value of the pixel.
Yeah, totally. We have found it to be not reliable enough for what we typically use for our deliverables.
Okay.
Color classifications, a lot of those automated point cloud classification tools, like I said, they work, they do a good job, but often not good enough for our levels of standards. Especially, I mean, heck, you can draft your different green ones, but sometimes you actually want to do vegetation. Sometimes you can know from looking at the photo photo that, yeah, it's grass, but it's grass that's been mowed to about 1/10 of a foot. So you can actually take that area and suck it down by 1/10 of a foot and then still use it, but the point cloud will throw it out. There are a lot of tools that help. And we're certainly not saying, go back to the stereo plotter days because that's the only reliable way. That's not the case. There are a lot of tools that help, but what we have found in our experience is the ones that promise you everything don't deliver on that promise. But they do a lot. So yeah, use the automated tools, but you still very much need a human in the loop if you're gonna get survey grade accuracy out of your drafting step. So yeah, even with that, even if you use pixel classification, you do need to manually go. You need to make sure that when it cleaned and classified that it did it properly, that it didn't throw out data that you want or include data that you don't. That all happens. But all of that is what we call part of that in-house drafting step, that you have humans in there that are doing the manual, either point cloud classification, point extraction, Linework drafting. And doing that in-house, high accuracy, reliable known product, and a lot of control over the process. But it's expensive labor, it's time consuming, and often no specialization. The people that are doing this usually have other jobs. They're surveyors, they're flights, they're pilots, they're engineers or CAD technicians. And the other option, another just minor plug for Aerotas as well, is hire a drafting firm because that can be affordable at any scale. You don't have to spend $10,000 on a software license. You can spend a couple $100 on a project. They have excess capacity that they can, put 10 people on a single project for 2 days if needed. And specialization. So our firm, for example, we have people that are specialized at every step of the process because we have scale for this. So we have flight ops managers whose whole job is mission planning, doing that sort of thing. We have photogrammetrists whose whole job is the photogrammetry step. We have CAD technicians and GIS techs that actually are doing a lot of this really, honestly, low-level grunt work, digitization, and data extraction. And then we have engineers that do a lot of the CAD finishing, which is going to be that final step that I go over. Obviously, the downside, no process control. You are paying someone else to do some of this work, but we like to think it's a pretty good option for actually getting a lot of that kind of grunt work out of the way. And ultimately, it's still on you guys to, as the surveyor, to work with the data and seal it, because that's your reputation on the line. So we totally understand that. All right, so let's talk about the different methods of line work drafting. We're talking about one working in a point cloud, but that's certainly not the only way to go. One option that we honestly don't love, but is out there, is to draft on individual photos. This is possible in Pix4D. There are a few other softwares, one called Datamate as well, that does something like this, where you're actually identifying points in individual photos. This is extremely accurate because you're actually triangulating individual points from multiple photos, but ridiculously time consuming. Imagine like when you're marking a ground control point in multiple photos, doing that for every point that you want to extract out of the 3D model. You're going to get the highest quality data, but man, so time consuming, it's absolutely worthless in our opinion, but it exists. You can draft directly onto the ortho photo itself. You've got your high resolution ortho photo, so you're actually going to be drawing your 2D polylines on the ortho photo. This is a clean process, it's pretty easy. It can be done in a lot of GIS softwares. It can be done in a handful of survey softwares as well. Civil 3D is actually probably the worst software to do this on because it doesn't handle big, large files well. But it's great for quick 2D data extracting a few points. Point cloud drafting. You can work in the point cloud itself, extracting individual points, drawing polylines, drawing curve lines, blah, blah, blah. Might be up there with some of the higher accuracy options. It's very, very highly accurate. The point cloud's an extremely rich data source, but it's also among the more time-consuming options out there. For anyone who's worked with the point cloud, they'll know, yeah, it's good data, but yeah, it also takes a lot of time to process and post. And the other is 2.5D DEM orthophoto drafting. That's going to be for some of the other softwares out there where you input both the orthophoto and the surface model, and you actually draft your points, polylines, break lines on top of that. That's probably our favorite for most of the work. It's a good balance between accuracy and efficiency. Now, what's the best one? This is another one of those trick questions. I've been doing that too much this morning. But what's the best method for line work drafting? Well, they're all different tools for the right job. 2.5D is going to be really efficient for topo, but it's not going to be able to look under trees or even sparse vegetation causes problems with that. It's not going to be able to look even a little bit under eaves. Point cloud is going to be pretty accurate. You can work under those eaves, extract a lot of good points, but it's going to take a lot of time. Drafting directly on the ortho photo, super, super efficient and fast for 2D line work drafting. Doesn't have any 3D data to go with whatsoever. Drafting on individual photos, if you have a few really hard to get, really difficult points that are underneath buildings or through trees, yeah, they're great for getting maybe just a handful of points that you can't get otherwise. But other than that, insanely time consuming. A good workflow will actually have processes and procedures in place to use all of these tools when necessary and have them at your disposal. There is not one best solution, and in fact, as part of a good kind of drafting workflow, you will get what you can out of each different layer. You will draft 2D data on the ortho photo, you will draft your topo data and create your surface data off of the 3D data, either the point cloud or the ortho photo, and maybe if you do have those high accuracy points or hard to get points that were only in a few photos, you get them on individual photos. There's no best option. That said, there are bad options. One thing, importing an ortho photo directly into Civil 3D, we don't like that one bit. It's messy, and what people often do to make that work is they'll heavily degrade the quality of their photo. They'll compress it, they'll downsample it, or do whatever it takes to actually get it to open in Civil 3D. From our rule of thumb, Civil 3D breaks down, depending on your machine, at around 3 or 4 gigabytes uncompressed per ortho photo, which a lot of big projects easily break that. But you should never draft on a downsampled photo or a compressed, any sort of compressed photo. Note, you're losing your resolution, all that work that you put in to getting your ortho photo high enough accuracy, you're then just throwing maybe half of that out the window by downsampling. The other thing that I see, unfortunately very commonly, is what we call dumb decimation of the point cloud. You get your big giant point cloud and you say, great, I have all of this wonderful data, but it's too big to open in my software, so I'm just gonna cut out 90% of the points. And I'm only gonna take 1 out of 10 points, make it a sparser point cloud so I can manage it. That's ridiculous. You're getting rid of you're getting rid of so much of the valuable data and fidelity that you need. If you wanna try drafting a curb line, which you can do in other methods, when you decimate a point cloud, that curve just becomes a total slope. It's worthless. You're reducing your fidelity. So we are very much against dumb decimation of the point cloud or anything where you just kind of cut out huge swaths of data. Same thing, importing the ortho photo directly into Civil 3D. That's great for printing. That's great for context. That's great for actually creating a sense for backing up all the rest of your line work. Wonderful. Fully supported. Good idea. Drafting directly from a compressed ortho photo on Civil 3D, not a great idea, in our opinion. All right, so we talked about our 4 different methods of line work drafting. So what are the different softwares that you can use out there? So here are a handful of the more popular ones. GIS, ArcGIS is good for some 2D drafting. TopoDot is great for point clouds. 3D Reshaper, Autodesk, Revit, VR Mesh can all be used for point cloud processing as well. Virtual Surveyor we really like. It's one of the 2.5D ortho drafting methods. Global Mapper also works for 2.5D and also has a point cloud module as well. What's the best one? We have all of them, different tool for the job. We have our preferred ones, Global Mapper, ArcGIS, QGIS, Revit, and Virtual Surveyor are some of the ones that we use most commonly. But again, it's about the best tool for the job, and each project site's going to be different, depending on the type of terrain, depending on how much vegetation you have present, depending on whether or not you're doing a 2D only ALTA survey or whether you actually need contours. You got to pick the right tool for the job. But ultimately, the downside of a lot of this stuff is that line work is it's time consuming. There's no way around it. All of these softwares, like I was saying, a lot of those automated softwares, they're not quite there yet. These are some examples of just some of the projects that we tried to time to say about how long it takes. 14-acre ALTA survey, it's going to take probably about 7 man-hours of just raw drafting. That's going to get you your topo, your curb lines, your utility access panels, your edge of pavement, concrete, building drip lines, whatnot. Another one example, 140-acre topo. You can see 10 times as much land to cover, only about twice as many man-hours. Obviously, simpler data, simpler workflow when you're just getting topo. But again, you got to clean it. There's going to be a lot of vegetation that you just need to avoid. And there are some automated tools that can say like, okay, hey, here's this big swath, let's take only the low points. And those are good tools, they really help. They help speed up that drafting process, but they're not the magic bullet. You take a lot of those low pass filters, they're not only gonna find out the gap between bushes, they're also gonna find out any artifacts really easy. Any artifacts where you have one of those down spikes in the surface model. That any of those low pass filters are just gonna drop right to the bottom. So you need to have a manual drafter to look at those as well and pick them out. That kind of goes back to that photogrammetry side that there are errors throughout every step of the process. And that's not a bad thing, you just need to be aware of them and manage them. 2.5 mile corridor might take 15 man-hours to do some proper cross sections and get good topo, get all of your break lines, curve lines, that sort of thing. Single family home, you can do a complete survey on it in 2 hours, honestly probably less than that. So that's kind of the line work drafting phase in a nutshell. But we're not done yet. That's, at this point, we typically are just going to have points and polylines. That's going to be about it. DXF format, maybe not even the right layers that you guys use, not the right colors. You can put it into CAD pretty easily, open it up in any CAD format, but you got to go to the next step, CAD finishing. CAD finishing, what we say, that's the step of going from raw points and polygon lines to something like this, to a finished survey. This is one of our actual clients' surveys that they delivered. The ortho photo was used with our system, and I think probably 70% of the actual line work on here was done with the drone, and 30% was done on the ground. But as I mentioned, kind of indistinguishable from any normal survey, and you can't tell which was done on the ground, and which was done in the air. I can almost guarantee that all those parking stripes in the bottom right were done with the air, because it's parking stripes. If that's, a couple tenths, it's not the biggest deal in the world, but it's still going to be a 10. And things like building corners and property boundaries, obviously going to be done in the ground. So what do you do with the drone? What do you do with in the field and using traditional survey methods? This is a kind of rough breakout for how we like to deal with that mixed, with that mixed workflow. The drone data is going to be great for topo points, break lines, paint striping, edge of pavement, curves occasionally. That depends on how high you fly on the type of job site. If you fly a Phantom at 400 feet, it is not going to be good enough to get 3 or 4 accurate curve lines. You might be able to get back of curve and kind of edge of pavement in front of it, but you're not going to be able to get top of curve or gutter at 400 feet. At 100 feet, you actually can. But that's the drone data. Field data, obviously the stuff that is legally required to do on the ground, things like boundaries, building corners where you typically need higher accuracy, and there might be some obscured shots from the air. Any monuments, ADA compliant shots, if you really need to have accuracy better than 1/10 of a foot. So for ADA compliant curves, we definitely recommend doing that on the ground as well, and any obscured areas. This is a big part of creating that kind of reliable workflow as well. Having your field crews know what to shoot on the ground. This definitely comes with experience, right? That the first time you send a crew out and say like, oh, only gather these things, they might miss a few shots, and you can usually pull that out of the drone data as well. But creating that reliable, standardized workflow, and heck, even using checklists a lot is really reliable so that you know this is what we get with the drone, this is what we get surveying on the ground. So you take all that, merge your data, throw your drone data, you have that DXF file, your points and break lines, you've got your field data, so you throw it into CAD, create a surface. That's going to be the next step. There are just some basic conversions, nothing really special here, going from just 3D points, maybe in a CSV format, to smart points, actually creating a surface, getting your contours generated with your colors, your layers, major, minor intervals, notations, blah, blah, blah. Applying all of your custom layer templates as well. I'm sure each one of you has your own custom layers, and heck, even individual clients have their own needed layers. Improving visibility and usability. Adding your symbology for things that looks like trees, adding notation so that when you're actually looking at a survey, that it actually works, or that you know what you're looking at. A lot of times the raw stuff that comes out of the raw line work drafting phase, especially if you are using, heck, almost any of those softwares, you're just going to get points. Maybe you are going to get points in a code with it, but sometimes not even that, it's just going to be an XYZ point. So adding your symbology to it, and that sort of thing is pretty important. And then adding in your CAD-friendly imagery. We've talked about this before, that adding full resolution ortho photos into CAD just does not play nicely. So creating and compressing a CAD-friendly ortho photo is the next step, which is going to be something that we usually recommend less than 200 megabytes of imagery per project. Beyond that, it just becomes a pain. If you want to share it with someone in the other office, you can't, send over a 10 gigabyte file too easily, and only the highest end workstations can even open it. So using good compression algorithms, we use QGIS. It's an open source GIS software for some of their image algorithms, for image processing algorithms to actually compress some of these huge ortho photos into more CAD-friendly formats. Also used for cropping the outer edges, making them clean, getting rid of the artifacts that might be on the outside of a Pix4D processed image. And these are going to be optimized specifically for context and printing. So again, the idea behind this is not that you would use this ortho photo for drafting. In fact, if you zoom in, it is a compressed image. There will be data loss as part of that. And when you zoom in, it's going to be a little bit blurry. So that's why you ought to do your line work drafting. Any of your drafting and data extraction ought to be done on the full resolution data. And the CAD-friendly ortho photos and that sort of thing should be optimized specifically for printing and context. Obviously, looking at this site right here, you can see exactly what it is. Where's the building, where are the parking lots? It just gives you that kind of context. But it's in a format, for this one, obviously I can put it in a PowerPoint, so it's just a couple of megabytes. The full resolution version in CAD is going to be, like I said, a couple hundred megabytes for a 50, 60 acre prep site. And of course, that gets you to, once you have all of that, and you've done all of the other work that you guys do as surveyors, you've got your final survey, which, again, final survey deliverable. I say it again, should look the same, whether made conventionally or with a drone, or best, with a hybrid workflow. All right, so now we've made it almost to the top of that pyramid on the journey. So we've gotten through our CAD drafting phase, and we've actually can get good data. Now this is all wonderful. Let's say we did our first project, we've spent a while, we've gotten there. But if you get to this point, and it took you 200 man-hours to get to this final survey deliverable, you still don't have a good survey program yet, a good drone survey program yet. Because if your drone program isn't saving you time and money, it's not working. It's still a research project. We don't like research projects. We like projects that actually make us money. And drone programs should actually save you time and money. And that means you need to create efficiency in every single step of the project. And I've referenced a lot of this throughout, but that means from the planning, knowing what flight planning, what overlap you're going to fly. Do you take an RTK aircraft or a non-RTK one if you have it? When you set your ground control targets, who's setting them? Who's shooting them? What are you using to shoot your ground control points? When you collect the data, having a good procedure so that you go out and hit fly and don't say, and don't just grab data and hope that something good comes out of it. And then obviously photogrammetry, Linework, and CAD, and all the QA stuff's in there as well. There should be efficiency and repeatability baked into every step. And the best way to do that, standard operating procedures. Create standard operating procedures for every step. Mission planning, ground control, field data collection, pre-flight setup, all the way through to the inspections. I did a course on Part 107 yesterday and was big on checklists. They're good for safety is a big part, but they're also good for all of those little things that just become time killers. I think some of the most frustrating jobs and sites that I've ever been on when I was starting out in the drone industry is if I had driven 2, 3, 4 hours to a job site and forgot a memory card. A tiny friggin' piece of plastic the size of your pinky nail. And you lose 4 hours because you didn't have that friggin' memory card right. And I'm sure this happens to all of you guys too. You forget antennas, you forget to charge your batteries, blah, blah, blah. Standard operating procedures save time and money, and they prevent the stupidest little mistakes that just make you want to die. Yeah, so we really love checklists. We're big fans of checklists, both for safety, but really from that time and money perspective too. It makes it repeatable, it makes it reliable, it makes it that whatever crew you send out, they're getting the same data because they're following the same procedures. As part of that, with creating these SOPs, you should know beforehand what your desired outputs are. The biggest time killer that we ever see is, let's just see what we can get out of it. Hey, let's fly the drone and let's see what we can do with it. Can you imagine the concept of sending a crew to a job site with some tools and say, let's just see what they come back with? Maybe we can put a survey together out of it. We'll see. We'll just say, here, spend 8 hours out in the field. Here's a GPS, here's a total station. Good luck. We'll see you later. They come back, they're going to have just all sorts of ridiculous. They're going to shoot the wrong points, not the ones you need. Know what your desired outputs are. Don't make this a science fair project. Let your kids do that. So this concept of let's see what we can get out of it. Let's try it. That's how you just kill yourself in time. And you might get good data. You might get really good quality data. But you're not going to save time. You're not going to create an efficient, repeatable workflow. If you try and do this, we see this all too often. People spend tons of money, oftentimes hundreds of thousands of dollars on this drone stuff, but it will never break that final level into a reliable, repeatable, valuable workflow because it costs more money and takes more time than surveying on the ground. And if that's the case, if it takes more time and costs more money than it does to survey it on the ground, then that $100,000 drone or $5,000 drone, whatever it is, it's just going to gather dust in the closet. You're not going to want to bring it out. If you're an owner, you're never going to give it to your crew because it's going to take them twice as long to do the same amount of work. So you've got to make sure that you know your desired outputs and use them properly. You got to pick the right tool for the job too. Drone is a tool in a toolbox. Does not do everything. Like I was saying, if all you do is boundary survey, nope, drone's the wrong tool. Might want to fly to site to get that extra data if you're using it to impress your clients to have the ortho photo backing it. But if you're doing boundary, wrong tool for the job. You guys have a truck full of tools. Metal detectors, GPS, total station, staking, whatever. Tons of different tools. The drone is one of those tools and should be treated as such. It is not something that creates magical surveys out of 15 minutes, but it sure does help a lot if you do it right. Other just kind of basic considerations as well. Plan for data storage. These things can create a huge, huge data footprint, so make sure that that's integrated into your operation as well. 10 acres at 100-foot AGL can take as much as 5 gigabytes of raw photos. The interim photogrammetry outputs are 15 gigabytes if you're going to archive that as well. 2.5 gigabytes of final output data, plus obviously all of the other compressed stuff. Data